You have your last quiz is scheduled for Monday, and it is over sections 9.1 and 9.2, which we're going to look at today, but I'm going to do all of the works on the calculator. As we saw, it's really a laborious, and you'll see when we look at the notes, the actual formulas can be rather time consuming if you're not using either a graphing calculator, what we're going to use, or a statistics package like SPSS or Excel or something like that. Well, Excel can do statistics, I guess I should say. Then probably you're going to be sort of happy to hear this. I had planned on May the 3rd having test 5 over the rest of our material from chapter 9 and 10. I'm canceling test 5. Woo! I thought I heard that. No, that was me. So I'm going to cancel test 5. You will have a quiz over the 9.1, 9.2, and then the chapter 10 stuff you'll see on the final is how I'm going to handle that. And here's why I want to do that. Because the week before finals, I want you to have an opportunity during class time to make up a low test and a low quiz of your choice. My plan is Monday, May the 3rd, you will be, and this is totally optional, all right? You don't have to take advantage of this if you're really happy with your grade. Monday is going to be make up your low test. And then Wednesday, which is the Demaeth of Cinco de Mayo, you're going to make up your low quiz. And then that Friday, the 7th, that's the last Friday before finals week, we'll go over the practice final or any other questions that you guys might have. Any questions on that? All right. This week, by the way, or excuse me, next week, what we'll do is Wednesday and Friday, we'll go over the chapter 10 stuff. We're just going to look at, again, it's going to be entirely on the graphing calculator. And then we will go over, if we have time to go over your test in class, I'll do it. If not, I'll make a video going over your test and I'll post it and email everybody, okay? And I see, what is that, a chat? Yeah, somebody's chatting with me. Look on the syllabus for your final schedule. It's on your syllabus. And I don't have it pulled up on this computer. And I'm kind of afraid to do too much on the internet because I might lose my connection. In fact, today, I plan on not even doing the smart board, in all honesty. So I got some just pictures that I'll show you of the concept. Hopefully that helps. Yeah, when in doubt, do this for all your classes. When in doubt, the final should be on the syllabus. All right, so let's get started. And I believe I have closed captions on. We'll find out. Yeah, should be on.
Between two variables, that doesn't automatically mean
sorry. I'm trying. I always try to skip the intro.
Can often be deceiving. Although we might observe a strong association between two variables, that doesn't automatically mean there's a cause and effect relationship. One of the biggest challenges in attempting to prove causation comes from hidden factors. They might not immediately be apparent, they just lurk in the background, and that's exactly what we call them, lurking variables. For example, a study that found people who owned 2 cars lived longer than people who owned only 1 car. Those who owned three cars were even more likely to live a longer life, and so on. Does this mean buying more cars will allow you to avoid death? No, of course not. In this case, the lurking variable is the car buyer's accident. Richer individuals own more cars and tend to live longer, probably because they have access to better medical care and healthier food. The cars have nothing to do with it. Of course, sometimes causation seems to be the only reasonable explanation of the relationship between an explanatory variable and a response variable. We can see this in the case of smoking and lung cancer.
Brought to you by Winston.
Believe it or not, there was a time when cartoons sold cigarettes on TV.
Winston tastes good, like cigarettes should.
People smoked in hospitals, and smokers didn't give a second thought to the health risks they might be taking. A far cry from today, when anyone can tell you smoking causes lung cancer. It's even printed on cigarette packs. But how can we say for sure that smoking causes lung cancer? Yes, there's a strong association between the two, but how do we know there are no lurking variables affecting our conclusions? The best way to make a case for causation is to conduct an experiment. An experiment imposes a treatment in order to observe its effect. In the case of smoking, we could get a local hospital and randomly assign newborn babies to one of two groups, those we force to smoke and those we prevent from smoking. We could then keep our subjects in isolation and as they get older, compare the cancer rates between the two groups. The only difference between the groups would be their smoking habits. Of course, this particular experiment is highly unethical and logistically impossible. So if we can't conduct an experiment, how do we prove a causal relationship between smoking and lung cancer? The answer to that question is long in coming, but offers a fascinating look at biostatistical research. Cigarette smoking became increasingly popular in America after World War I, when cigarettes were handed out to soldiers to boost morale. Per capita consumption rose from 49 cigarettes in 1900 to 611 cigarettes in 1920. Along with the rise in smoking came a disturbing rise in lung cancer rates. A handful of doctors began to raise early warnings about the dangers of smoking. One was Richard Overholt, a young lung surgeon who noticed that his non-smoking patients had quicker surgical recoveries and higher survival rates than the smokers. He tried to get other doctors to encourage their patients to quit.
To show the doctors were smokers, they didn't believe this, and it was very difficult to convince people that this was doing damage to them because they felt that they were getting pleasure from smoking.
During the 1930s and 40s, the popularity of cigarette smoking soared as a new image of the sophisticated, independent, and fun-loving smoker took hold. Little thought was given to the risk, but in the early 1940s, new studies sounded a louder alarm on the dangers of smoking. One of the earliest and most compelling was a retrospective study conducted by Ernst Winder and his teacher, Everett Spring. Subjects were separated into two groups, those with cancer and those without. Their health status was treated as a categorical variable with one of two possible values, cancer patient or non-cancer patient. Both groups were asked the same questions about their past habits. Responses were compared to see which habits distinguish people with cancer from those without. Smoking stood out.
Dr. Winder, then a student in St. Louis under Dr. Rich Graham, came to me and he said, Camel cigarettes cause cancer of the lung. I couldn't believe it. And you see what you look for, and you look for what you know, and it never occurred to me that cigarettes caused cancer. So we went to see my patients, and at that time I had quite a large practice. We discovered to our amazement that patients who had cancer of the lung were 17 times to 1 as apt to be 2-pack-a-day smokers. So here was a fact. Now tell us something.
Despite the remarkable discrepancy in smoking habits between the two groups of patients, this so-called retrospective study was not good enough because the study looked at past behavior it could not control. It's possible that the lung cancer was due to any number of lurking variables. What if, for example, something in the smoker's genetics predisposed them to smoke and also made them more inclined to develop lung cancer? In this case, it wouldn't be causation, but rather a common cause, the smoker's DNA. Or what if the smokers lived in heavily polluted environments that might cause lung cancer? Their smoking habits would be confounded or tangled up with pollution, making it impossible to discern the true cause of the disease. But perhaps it was a coincidence that their cancer patients just happened to be smokers. After all, it was a popular habit at the time. Common cause, confounding factors, coincidence. These are all alternative explanations for a strong association between two factors that don't have a causal relationship. The next step in solving this epidemiological mystery is setting up prospective studies. Doctors Hanlon and Horn of the American Cancer Society gave about 200,000 people a smoking questionnaire and followed them for 4 years. Unlike a retrospective study, which begins with sick people, cancer patients, and works backwards to examine their habits, the prospective study looks ahead, following healthy people, both smokers and non-smokers, forward through time to see which ones develop lung cancer. It's still not quite an experiment, since people make their own choices about whether or not to smoke, rather than being randomly assigned to take up the habit. But it brings science one step closer to nailing down evidence of causation between smoking and lung cancer.
The preliminary study published in 1954 caused quite a sensation. It was the largest study on smoking that had been done. It was the first prospective study that was published, and it showed that people who smoke cigarettes have a lung cancer rate 10 times as high as people who never smoke, and that the risk goes up proportionately according to the amount of number of cigarettes that people smoke per day.
This high correlation was consistent with the findings of the retrospective study, but there is still disagreement about how to explain the correlation. Remember, those pesky lurking variables could be present, making the association only appear strong. To tackle this problem, doctors designed a follow-up study of 1 million people. The smokers and non-smokers were matched on such variables as age, geography, and occupation. The goal was to make smoking habits the only major difference between the two groups.
And we matched them on 19 different variables, so there was as like as we could make it. And when we finished this analysis, the death rate of the smokers was higher than the death rate of the non-smokers.
Even though the two groups were as similar as possible, they were not identical. Sir Ronald Fisher, known by many as the father of modern statistics, argued that without a controlled experiment, there is no way to know for sure whether the lung cancer was due to smoking or to another unknown variable. So despite the accumulating evidence from dozens of studies, from many scientists and statisticians, the labeling of causation is still premature. So they turned to the lab for help. Throughout the 50s and 60s, biochemical and animal studies provided compelling supporting evidence. Researchers painted tar on mouse skin and rabbit ears, causing cancerous tumors to develop. They also identified carcinogens in tobacco smoke, and lab work confirmed another aspect of the prospective studies, the dose-response relationship. By exposing hamsters to cigarette smoke, it was possible to determine how higher numbers of cigarette smoke is related to higher incidences of lung cancer.
So you have precision tobacco smoke. It is proved to be carcinogenic to animal tissue. It is highly correlated in retrospective and prospective studies in respect to cancer of the lung in humans, and that was more than sufficient to establish tobacco smoke as a cause of lung cancer and subsequently other cancers in humans.
For some, the evidence was sufficient, but the struggle to prove causation to a nation of smokers was not over. Rich, powerful tobacco companies did not ignore the growing evidence that cigarettes posed a serious risk to health. Instead, they set out to reassure the American public that their brands were safe through strategic advertising that featured doctors' endorsements and claims of being less irritating to consumers' throats. In 1962, the Surgeon General assembled an advisory committee on smoking and health. The goal was to take on the question of causation, Its task was formidable: to review more than 6,000 studies on smoking. Based on predetermined criteria, the committee concluded that the association between cigarette smoking and lung cancer was found in many studies with many different groups of people. The association was very strong. Cancer regularly followed smoking in time. Smoke did contain cancer-causing substances, and no explanation other than causation was plausible.
The committee states on page 61 of the report, and I quote, in view of the continuing and mounting evidence from many sources, it is a judgment of the committee that cigarette smoking contributes substantially to mortality from certain specific diseases and to the overall death rate.
In the wake of the Surgeon General's report, millions of Americans quit smoking. Congress passed a law requiring warnings on cigarette packs, and the anti-smoking movement, as we know it, was born. The scientific consensus was in. Smoking does cause lung cancer. Now you can see just how hard it is to prove causation when direct experiments aren't possible. Here, the non-experimental evidence is about as strong as it gets. Remember, not all associations can be explained by cause and effect, but some can. With enough evidence from enough different sources and the help of statistics, we can be confident in our conclusions. The public seems to be getting a message too. Under 20% of Americans smoke these days. That's less than half the proportion who did at smoking's peak back in the 20th century. I'm Curtis Sabetti for Against All Odds. Stay tuned.
Okay. Let's stop the share. All right, bear with me. I'm going to be pulling some stuff up here for us to take a look at. I'll pause the recording while I'm doing that. So what we have here are obviously the notes for section 9.1 and 9.2 is on here as well. So this was talked about in a previous video that we watched, but a scatter diagram is what graphically we look at when we're doing regression problems, and it's XY pairs. It's called bivariate data. You have an X value and a corresponding Y value. X is called the explanatory variable. Y is called the response variable. In other words, the value you get for Y depends on what you plugged in for X. And we are essentially linear correlation means we're looking at an equation of a line, Y equals mx plus b. So you plug in certain X values and you get certain Y values in response, right? I'll let you take a look at figure 9.1 on page 531 yourself. I am going to pull up an actual graphic example that's not in the textbook later. But the main idea here is to try to find the equation of the line that best fits the data and to use it to further examine relationships between X and Y. So one of the things we want to know is how correlated are they? Does it have, for example, a perfect positive linear correlation where all of the points perfectly fall on the line? Of course, that was me drawing this stuff myself, so they're not that perfect. Or is it a perfect negative linear correlation? Usually it's somewhere in between, okay? We'll look at the graphing calculator here. The instructions are on page 534, but I'm also going to go over it in here myself. So other than visually, we can use the correlation coefficient, which is represented by the letter R, to examine the strength of the relationship between X and Y. And R is a value, so let me zoom back in, sorry. R is a value that goes from -1 up to +1. The closer you get to -1, the closer you are to a negative linear perfect negative linear correlation. The closer you get to +1, the closer you are to a positively sloped line. Perfect positive linear correlation. And again, usually it's somewhere in between. The closer you get to 0, as your values get smaller and smaller, or I should say as your values go to 0 from either direction, that's not high correlation at all. Any questions on that? All right, and this is something important that was talked about, and I can't fit it all in here, so I'll have to go back out. This is an important concept, which is why I showed you that one more video on correlation. Just because there's a high correlation does not imply that X causes Y. More, well, it's more like, you usually see it more like this. Correlation does not imply causation. There could be other unknown variables at work that are referred to as lurking variables that cause the high correlation. And here's examples that you can look at in your homework, right? Let me pop something else up here. Oops, oh, wait, where is it? Here we go. So for example, if you have your lines on a perfectly, or your points on a perfectly negatively sloped line, that is r equals -1. If it's in general a negative slope, but the points are scattered somewhat, you'll be somewhere between -1 and 0. So here's an example of points with a correlation of -0.5. If there is no line that best fits the data, that's r equals 0. And then as you go towards the positive end, this would be maybe how an r of 0.5 would look. And here would be an r of 1, where all of the points are perfectly on the same line. Any questions about that? That's the idea with correlation. Now let me minimize that again. So 9.2, they actually go over linear regression. And what they use is called a least squares regression line, the line that will best fit the data. And what it does is, I'm going to got a picture of this somewhere. There we go. Let's see how much I can go in here. You've seen something like this on the video. What happens is you have a bunch of data points, right? And you want a line, and I apologize for the fuzziness of the letters here, but what you want is a line that minimizes these vertical distances between all of the points and the line. Those are referred to as residuals. The methods of that involve calculus and taking derivatives, which we don't do at this level, okay? So one of the things that you can do is take a look at those residuals. That's a residual plot. And another thing that was pointed out, you can look at something called a residual scatter plot, where you're looking at your values of R. Remember, they go from -1 to +1. And if, for example, you saw a bunch of these points or all of these points behaving in a certain way on one side of the line, that would indicate it's not a good fit. Or if they were, most of them underneath it, behaving in a certain way. What you want is a scatter like this, and not some kind of a visible, for example, curve that might indicate that instead of linear, it might be quadratic, that type of deal. Any questions on that? Bunch of background info you're getting here. Let's see. Now, your calculator, we can do, it's not a residual plot, but I'm going to show you also how to graph the data, because conceivably on a multiple choice quiz or final exam, you might have to identify the graph of the data as well, like the scatter plot, or somehow interpret the scatter plot, all right? Then we're going to get to this in just a little bit. This is an example we're actually going to do in class. But at any rate, so you do the least squares regression line. Well, that r squared, if you take that value r that we looked at, the correlation coefficient, and square it, you have something called the coefficient of determination. It's a measure of the proportion of variation in y that is explained by the regression line using x as the explanatory variable. In other words, how well does x explain the corresponding y value? The higher the value of r squared, notice it's squared, so it only goes from 0 to 1. All right, it'll never be negative. The higher the value of r squared, the more of the variation is explained, and that indicates a good fit. In other words, explained by the x values, whatever that explanatory variable was that you picked. The remaining percentage of the variation is unexplained. That's due to random chance or lurking variables that could influence y. So total variation equals explained variation plus unexplained variation. You don't need to worry about the formulas since you're not going to be using those yourself. All right. They have to add up to 1. So for example, if I found out that r squared is 0.7, then 1 minus that is 0.3, right? So the unexplained variation due to lurking variables would be 0.3. Any questions on that? All right. So let me pull this back up. Where is that? I think I can get rid of that. Let me get rid of those notes. We don't need those anymore. All right. So we're going to do this on a graphing calculator. And I'm going to zoom in for this so that you guys can see this better. Hopefully. Yeah, a little bit fuzzy again. I apologize for the poor definition of it, I guess. All right, now I have already entered this data beforehand because I have not done this since last spring, and I wanted to make sure this was the correct way to do it. All right, I was too lazy to follow instructions in the book. So here's what we're going to do. This data that we're looking at, where I got it from, that an image that I looked up under Bing Images or something, it didn't explain the experiment being done. My best guess is that you're looking at the height of people and their corresponding weight. All right. So height is going to be our x values. Weight is going to be our y values. So height is our independent variable, weight is the dependent variable. Or another way to say it, height is the explanatory variable, right? So here's what you do. And if you guys are doing this, in fact, let me ask right now, if anybody is actually going to be following along doing this, could you unmute and let me know so I won't speed through it too fast? All right, so here we go. You press stat, S-T-A-T. Go over to calc. What we want, check this out. You have an option. You'll notice item 4 says linreg, and that's linear regression. And notice it's ax plus b. This will put your answer in the form of y equals, they use a instead of m, okay? Y equals ax plus b, where a is the slope, b is the y-intercept, or the y value of the y-intercept. But if you arrow down to number 8, here's the regression as well, linear regression. Here it's in the form a plus bx, right? I use number 4 because I'm used to working with y equals mx plus b. You'll note that on this least squares regression notes, they use the a plus bx. It doesn't matter which you use. We're going to get the exact same numbers for the slope and the y value of the y-intercept. I'm going to use number 4, okay? I'm just going to press, oops, before I do that. Let's go back. Go to stat. First, you need to edit and put your data in. So stat edit, option number 1, edit. Make list 1 your x values, list 2 your corresponding y values. So I typed all of this stuff in before class that you see on the data set, right? Now we'll do second. So make double check your numbers, like on a test, or excuse me, the next time you see this would be on a quiz at the final. Double check those numbers you're plugging in, all right? And then you'll go to stat, you'll go to calc, option number 4, linear regression. Make sure your X list is list 1, and to get that, you would press second and the number 1, right? Make sure your Y list is list 2. You get that if it's not already there by pressing second and list 2. Make sure that X and Y list are set to whatever column list you put that data in. Freak list, ignore it. Ignore that. Go down to calculate, press enter. All right. Y equals ax plus b. My slope a is approximately 3.17, as you can see from the fuzzy notes over here. The value of the y value of the y-intercept to the hundredths place is negative 61.11, which you can see here in the notes. Any questions on that? First, we need to find the regression equation. All right, so this is like what you're going to be doing on your quiz next week, so it should be easy. So now check this out. Let's go to stat. No, I'm sorry, vars. Where's vars? Here we go. Go to vars and press vars. Notice option number 5 says statistics. Just press number 5. Notice at the top, the EQ. This is our regression equation. It's information that we just calculated. Arrow to EQ. Look down at number 7. It says R, that's the correlation coefficient. Now number 8 is R squared, but I'm going to show you a way to get R squared without having to go back through this to get to R squared, item number 8. But first, let's find the correlation coefficient. You'll notice they show it to you over here in the notes that I took a picture of. All right. So I'm going to press number 7. And R pops up, and I press enter. So that's approximately 0.96 to the hundredths place. Then rather than go through all of that again, going into the menus, just hit the X squared key. And it'll square it. And we get the 92.6. Well, yeah, 92.62 the way they rounded it off. Okay. And remember that R squared is how much is explained by the explanatory variable. So how much is unexplained due to lurking variables? I'll round it out like what they did. I'm sorry. I put the decimal in the wrong place. That should be point, because I'm not writing it as a percent. 9.262. So we have roughly 7% is unexplained and due to some kind of lurking variables. And then the idea is you would go back and try to see what kind of variables might be possible. Like, for example, gender could play a difference. I don't know whether these are male or female, to tell you the truth. I'm guessing male from the higher weights, but I don't know. And it could be other things that you would look at other than height and weight, like what kind of diet are they on or something like that. Do they exercise regularly, things of that nature. Any questions on that? Okay. Let me see if there's anything else I can think of I need to tell you guys. Yeah, I think that's pretty much it to get you through 9.1 and 9.2. So I will stop the recording and I will see you guys Monday. Be safe over the weekend and have a good weekend. And start thinking about a makeup test and quiz that you're going to want to make up the week before finals.
Mr. Shirkey,